I write a compiler for a small imperative programming language called Elna with Pascal-like syntax, and the compiler is written in itself, but it isn't finished yet. There is still a lot of stuff to do, and therefore in the compiler itself I can only use the features that are already implemented. So the language that I use is just an early version of the final programming language. And last time I was working on adding 2 new instructions to the intermediate representation, to the 3-address code. These 2 instructions are used to implement field access for records, for record fields. And these 2 instructions are copy to offset. This is this one here. And there is a similar instruction that is called copy from offset. So these 2 instructions are used to assign some value to a field of a record, or to get a value from this field. And for example, for assigning it to something else. I actually already implemented these 2 instructions, but the implementation isn't finished yet. So I still have to do some cleanup. This copy to offset and copy from offset instructions, they are very similar. So basically the first thing they do, they load a value. So they get some value and they load the address of this value with LA instruction. So this is assembly load address instruction. The compiler targets RISC-V. So assembly instruction, what is called RTL here, is basically RISC-V, the 32-bit version. So we generate load address instruction, then we add a static offset, so the field offset from the beginning of a record. And after that, for example, this is copy to offset instruction. So at the end we call a store word instruction to save the value at this offset, and copy from offset we'll call a load word instruction. This code here, this is the code of the copy to offset implementation, and we have also get address instruction. And these 2 instructions are actually very similar. So the beginning is very similar because they generate this load address code that loads the address of a variable. And I just copy pasted it to write the first implementation for copy to offset and copy from offset. But we should extract this code into a separate function, so that we do not duplicate so much code. And I think yeah, I can probably just modify this LNRTL get address instruction. Let me see where it is used. I think the only place where it is used is in this LNRTL instruction function, but probably if I add additional arguments, Then I need to define, well, we have here already this pseudo symbol variable and also an instruction. Since we see here a lot of code, yeah, I probably will just modify Elna RTL get address instruction, and if it causes that we need additional variables, a lot of code here in this branch, then I probably will wrap it into an additional function. Or we do it just from the beginning. So I have already Elna RTL operand value function. This function loads a value of its operand into a pseudo register, and here we will define operand address function. It will have almost the same signature. So we copy the variables here. And the first thing here, we get the address of the first operand of a TSC instruction, but I think it isn't always the case. So if we go to copy to offset, then it gets the address of the second operand. So we need to pass the operand which address we need. Let us call the variable addressable, and it will be actually a TIC operand or a pointer to it. Okay, then we can do a lookup. And instead of this instruction operand, we put this addressable operand here. So, and we dereference the pointer. And put it into a single file. I have implemented, I almost have not any error checking. So if there is a syntax error or something like this, the compiler will just crash. And therefore I recompile the code pretty often, so that I do not do any mistakes. Error checking still has to be implemented by, I suppose, a bit later. So then we generate a new instruction, a pointer to it, and at the end we will append this instruction to the instruction list. We can also return this instruction, I think, but let us append it. And now we do need this check. And this is actually the second thing, is basically this is actually wrong. So the first operand this addressable, no, this is fine. So yeah, then we check whether this operand is a global variable or a local variable. The difference is that global variables are not in the symbol table, so they are written as is, and the linker resolves them. Then and local variables are in the symbol table with their stack offset. So we generate this instruction, and then lookup is already done here. Then we check whether we find this symbol in the symbol table, and as before we replace this operand to access with addressable. And in one case it is a symbol, and in the another case it is a pseudo register. I probably should write the value here from the symbol table, but we will test it later whether it works. And then we append this instruction to the instruction list. And we also need the target operand here. And the target operand, so this copy to offset function uses an additional target operand that is generated. But for example, the get address instruction doesn't generate an operand. It just takes the first operand, or in this case the second operand of the instruction. So we also need to accept the target operand as parameter. Let us put it here in self as well, target operand, and the target operand is a pointer to an RTL operand. And then we can set the first operand of our load address instruction. Exactly, and that is probably it. And we have a syntax error somewhere, I think, because the compiler crashes right away. Not a syntax error, by target operand is a pointer in this case, so we need to dereference it, and it still doesn't work. And addressable is of course a pointer as well. Okay. Then I want to add a return type to this function. It will be Elna RTL instruction. And we will return this instruction at the end instead of appending it. And now we can try to rewrite the get address instruction using this new procedure. So Elna RTL operand address. We pass instructions, TIC instruction, variable map to it. We pass a pointer to the first operand first, I think. Yes. A pointer to the TIC instruction operands first one, and to the second operand where we save the result. After that, theoretically we do not need this check anymore, but we still need to append this instruction. So I can remove this part. Undefined reference, RTL operand address. And that looks fine. Now we can completely remove this code, and we can also remove this pseudo symbol and the variable as well. We do only need the instruction. Now we can remove the variables that we do not need. So actually the instructions and TIC instruction are not needed because we pass the operands one by one. That means that these two can be removed. And it should still work. Okay, and I think that I will get rid of this getAddress function. Or I won't. Yeah, let us just move this code here and remove this call and remove the function. And now we are going also to modify the two remaining functions, so copy to offset and copy from offset. I will have to find the new function here. It was operand address. So that we can look into the signature. And here we generate a pseudo register, and then we call the operand address function. We pass variable map to it. The variable map, the source operand is in this case the second operand. So this would be the address of TSC instruction operands 2, and the target operand would be basically this target operand variable, and that's it, I think. So we can remove this part and this as well, and we need to append the instruction. And it works. Then we can remove this code. So that's fine. And the last one is copy from offset. It should be actually also very similar, but it passes probably the third, no, also the first operand. Okay, elna RTL operand address. The first is the variable map, then we have the addressable, so to see instruction operands 1, and the last one would be the third. Oh, this is actually not fine. I passed the variable of operand type to this function actually. Yeah, we need to fix it. I shouldn't remove this getAddress function. This is actually wrong. The TSC operands and RTL operands have almost the same layout, therefore it works. And we do not have a proper type checker yet, but this isn't fine. And now we do here the same, just for testing, and after that we bring back this getAddress function. So I pass the third operand to it, the address, and I hope this will work. I think I haven't removed the local variable from the previous function. So we do not need this pseudo symbol anymore. It can be removed. Yeah. So that works, I suppose. Here I have one space. Too much. Let us go back to this copy to offset function. Here we do not need this pseudo symbol anymore. So this can be removed. And let us see where the getAddress function was. I actually replace this with RTL operand, so it just goes after the RTL operand address. Exactly, so basically here. And let us copy the signature here. And this is the run function, of course. So we do not need this pseudo symbol variable, I think, but we do not need the but we do need the instruction. And the code of this function is this. So we get the address of the operand and we append the new instruction. And here we just call this function RTL get address, and we pass the same operands to it. So we remove these two, and we pass the instructions and the TC instruction to it, and then the variable map. Now we create a new variable RTL operand of the type ELNA RTL operand. And the first thing that we do, we call ELNA RTL set operand, RTL set operand, and this is run operand set probably. ELNA RTL instruction set operand, but this is actually a different thing. Yeah. It sets an nth operand of the instruction, but we already have an operand. So what we do, we just set these values on the operand. So the kind of the operand is ELNA RTL kind operand pseudo. its value is int length, and its value matches the value of the TIC operand. In this case, it would be the value of the second operand and the length as well. And now we can pass this instruction, this operand, to our new function. And now we have to do the same thing for this offset function, but not here, but in the bottom half. What was it? From offset or to offset? It was from offset. So this is actually the same. We define it, but we use the third operand and not the second one, and we pass it to this function. Another thing that we need to look into is the generation, the instructions after the getting the address. So I generate an add instruction to add an offset to the address, and then, for example, load word. But actually what we want to have is we want to merge it into a single instruction. The last operand to an ATL instruction is always 0. This 0 is actually the offset. So instead of generating an add immediate instruction, we just want to save the offset as the last argument to the load word or store word instruction, and then we get and when we can get rid of an additional add immediate instruction. But I think that I haven't implemented these offsets yet. So we need to find somehow how do I write the offsets. I have them, for example, for store word instructions. And now alloc store. This is the prolog. But this is actually the place where we write them. RISC-V, ELNA RISC-V functions are This is the pass that actually writes the final assembly to the standard output, and then it is compiled by the assembler. Exactly, here we write the instruction name, and after that we should write the arguments with this ELNA RISC-V operand function. And this function checks. So here we write an immediate. Here we write a symbol, and here we write a register, and we just pass register name. And here we write memory. And basically if the type of the operand is a memory operand, then we write the offset, then parents, and then the operand value that would be a register in this case. But we also want to have offsets from pseudo registers, and here we use actually both fields offset and the value, and here it would be actually pretty similar. Yeah. The offset itself is in TIC instruction operands 2, and for both things, for the load word and stop word instructions, it would be the second operand that can contain an offset. So let us write it in here. It shouldn't break anything since it is ignored basically. But this is always a pseudo register, and we can find a stop word right away. So this is then copy from offset, or we can begin with a single instruction and then we can migrate the second one. So the next place we are going to search for is the register location, because we need to replace this pseudo register with a real with a hardware register. Log this is probably this instruction. It is called if the load address is called with load address, and loart is called when we encounter loart word. And in the case of loart word, we check what is the second operand. And if it is a pseudo register, and in our case it will be a pseudo register, we allocate the value of this pseudo register, and we create a memory operand with the offset 0. And we also insert a new instruction. What is this new instruction actually? So, what? And here we have the counter. So we need to load the value in this register from the stack. And here we copy this instruction. These are basically then two load word instructions, if I understand it correctly. Because first we need to load the value from the stack. So the address itself is saved on the stack. We load this address and then we load the thing that is on that address. And here we use the stack pointer. So this is the instruction where we load the value, the address from the stack. And this instruction should be actually then the thing that loads the offset. Where do we have the offset of the variable? The offset is actually in the same instruction. I reset it here to the counter. This is fine. I hope the instruction isn't overwritten here yet. So we just need to get the offset from this instruction. This could now crash because we will add the offset twice. Exactly. But if I go to this copy to offset function, it was copy from offset. And remove add immediate. Then it passes the final test. So we can now remove this instruction completely. And now the same goes for the store word instruction. RTL copy to offset. Here we do the same. So we pass this value as the third argument to the store word instruction. 1 second. And I break the line here, and we set the offset. We remove the add immediate instruction, and now we need to set this offset on the store instruction, and it is here, and it is actually almost the same, but we use two temporary registers, so we check for the second operand and we generate a store word instruction. Here we need two instructions, load word and store word, because we need to load the operand address from the stack first. And after that we get this address, and here we need to set the offset. And the offset will be actually the same, so we pass the instruction as argument. It means we can just get the second operand and we can get its offset. And it works as well. Now we can remove this add immediate instruction. And we do one final test. Fine. Now let us compare copy from offset instruction with load instruction, RTL load, because they should be almost the same. And for example, for load instruction, I actually pass they are not the same. Okay, I thought that maybe one can be replaced with another one, but I think it is not the case, so they are a bit different, I suppose. I probably could do the same here. Will it work? So that I just load the value into the RTL operand and then do load word instruction. The second part is similar because it generates this this lot instruction, but I think it is not worth it to extract it into a separate function, at least now. Never mind, we leave it as it is. One thing, every time I call this elnar_rtl generate pseudo function, I pass value and length separately to it and set the operand kind to pseudo. Actually, it would be more correct to set the kind in this function itself. So let us see where it is called. So here it doesn't send the operand kind, but it is set here. The same RTL operand kind is probably set here. And it isn't used this often. Let us add an additional argument to it. This argument will be operand, and its type is elnar_rtl operand pointer. And now we want to pass the rtl operand pointer itself to it. It is a pointer already, I think. Okay, and now instead of using the operand value, we will use the operand itself. So this one will look like the reference operand value and the reference operand length, and that is probably length is used here once again. So we replace it as well. With a bit of luck, it should compile. And now we can remove these two arguments that are bad typed anyway. I have to move this kind assignment so that we do not assign things twice. Oh, of course, I do not set the type here, the kind here. Instruction kind, this is Elna RTL generate pseudo. And of course, as first thing, we need to set the kind of the operand. Okay, looks better. This is the function that we have just fixed. This is the next one. We can just remove this line. Then this one. And that's it, I suppose. So that is done. This function generates pseudo register. We have a similar function in the 3-address code generation, which is also called pseudo, I think, but it does not generate a pseudo variable. It generates it doesn't generate a pseudo register, but it generates a variable. In the early stages of the compiler, the 3-address code also worked with registers and with hardware registers in the beginning, but it is not the case anymore. So the 3-address code is completely separated from the hardware implementation. So we can remove this function to make variable or generate variable. Let us call it make variable, I suppose. I do not know how often it is used. I think that we can just rename it with a regular expression. Elna TIC generate pseudo, and we call it Elna TIC make variable. And since I still have some time left, I will start to implement the last instruction that I can think of that I need in my 3-address code representation. And this instruction is at pointer. The current state of the things is that if I add an integer to a pointer, then it always advances the pointer by 1 byte independent of the type of the pointer. It is not how it is supposed to work. So if we, for example, add 1 to a pointer of some time, then it should advance the pointer by the size of the pointer type, not the pointer type, but the base type of the pointer. For example, here I want advanced current entry is a pointer to ELNA symbol entry, and I want to advance it by size of the type ELNA symbol entry, and I add this size to the pointer, but actually it should be this instead, so it should be enough just to add one, but it won't work currently since, as said, one wouldn't add the size of the base type, but it would add 1 byte. Therefore, to implement it, we will add a new instruction, add pointer, which adds not 1 byte, but the size, the base size of the pointer. And I will see later how I do it, because the previous stage of the compiler won't be able to compile the code. We probably need some transition step where we use a different operator for the pointer addition, and after that we can replace this temporary transition operator with addition again, so that the addition can handle numeric addition and point addition as well. But we won't be so far today anyway, so I will just begin. And we go to the LNTIC operators, and we just need to add here a new operator, probably before this nope, and this operator will be at ptr. Then we have this LNTIC binary expression. It converts a binary expression from the abstract syntax tree into 3 address code, and it actually it checks for the operator, and in each branch it creates a TAC instruction with the specific operator, and then it sets the operands. Because the operand setting will now differ for addition and subtraction from the other operands, we will need to move this operand setting to the branches itself. But since we do not want to repeat the same code each time, we will need to define a new function, or basically 2 functions. The one function for addition, plus and minus, and another function for all the other instructions that are handled the standard way. So binary expression as name is actually fine, because it is the name of the parser node that we get. Let us call the function LNTIC binary. It is probably something like binary operation, binary create. I cannot think of a better name, to be honest. So what will this procedure do? This is actually fine, so we generate the code for both sides of the binary expression, for both operands. And we need to generate an instruction for the operator itself, and the operator, we will receive the operator as the first argument to this function, I think. So here it is LNetAC operator, is LNetAC operator, and we will pass it in here. After that, we will generate a temporary variable, and I suppose we will get it as argument, the same as here. So, and we will copy this parameter from here. And I can probably split the line. And then we need to set the operands. So the first operand is, of course, the target. The first operand is the target. We need this instruction variable, so we copy it from here. And this is already fine, and then we set both LHS and RHS left-hand side and right-hand side operands for this instruction, and then we return the instruction. So the return type of this procedure is a pointer to LNetAC instruction, and then we need 2 more arguments, LHS, LNetAC operand, a pointer, and then RHS, also a pointer. Also here we can split or move some arguments to the second line, and then if we use these operands, we need to dereference them. And this should be fine, but it isn't. Oh, we do not have the symbol table. We do not have the symbol table. Exactly. And now we want to replace the code in each branch with the call to this function, LNetAC binary create, and we put it just in here. pass the operator to it, and LHS, RHS, symbol table, and operand. So LHS, RHS, and symbol table, and the target then. Now we can test whether this procedure works. It will actually return the instruction. So we will generate the variable 1 second time, but it probably won't hurt. Yeah, that works. Actually, I want to save the current progress before I have broken something, just to be sure that I can restore the previous state if needed. And now we can just replace all the instructions here. Okay, and that's it. And now we do not need these instructions here, or these statements. And the code still compiles and passes the final check. Now we can, we will copy this procedure once again. But rename it and call it sum, for example, or it could be addition or something else, what do I know. And in these two cases where we do plus or minus, we use sum, create, and subtract as well. Okay, that looks fine. And as I said, because this stage of the compiler should be compiled by itself, and the previous stage we cannot use the plus operator right away. But we will probably, I think that I have a pipe operator or at least a token pipe that isn't used anywhere, and we will use the pipe for the point addition. And after we implement this point addition in the next stage, then can replace the pipe back with the plus sign. I only define the token here, but I do not really set it. Pipe token is a single character token. Somewhere I will check the character literal. This isn't it. So for example, here we have the head symbol. This is parser designator. No, this is the parser. We do not need the parser, we need Alexa. Arrow. Exactly, here we tokenize single character tokens. These are used. This isn't probably used as well that much, but well. Yeah, let us just check whether the current character we are looking at is a pipe. And if it is the case, then we do an Alexa token create an Alexa kind pipe position. I could probably also implement it in the previous stage so that we can already begin to use this stuff in this stage, because it shouldn't be difficult. It will be handled almost the same as addition. Or probably we can just start a new 21st stage. So now we can tokenize this thing. The next is the parsing, and we need to find the place where we parse binary expressions. Let us add it here as well. So this is in the bottom half. This is the previous stage, the stage 19. We look for the classify single function and just add the same branch here. So here we have the plus token. And here we have the plus token, and we just copy this branch, add else to it, and we check whether the kind is pipe. And if it is the case, then we advance the tokenizer and parse. All these are unary. No, these aren't unary expressions, but we pass probably the right side of the expression, which is not. And if we have parsed something, then we create a binary expression node, and we set the operator to the actual token. This isn't that nice. We probably should have defined an additional enumeration for the operator type, but well, it is as it is for now. So we have the pipe, and we have everywhere basically the same code. It takes the operator from the current token kind, and it saves the token here. And RHS node does not have the correct type, I think. And now parse the unary expression. It returns the result, and result has this type. I actually doubt a bit that it always returns a unary expression. Okay, the types should be fixed later, but it is definitely not 0 but nil, because it is a pointer. RHS node. This should be actually just some expression and not unary expression, I would think. Oh, this is the previous stage. Yeah, but here we see the same. Okay, that doesn't matter for now. Let me find again this function. So we have the token here, and we can define actually the operator and just write it here, or handle it later. We also add the same branch here after minus pipe unary expression. Then we try to compile it. Then we have name analysis, and then we have type checking. The type checker doesn't really check types, but it sets the type for each for each node in the abstract syntax tree, they should work independent of the operator. And the next path we are interested in is actually the intermediate representation. So in this case, exactly, we check actually the operator and call the instruction just to make it compatible so that we can use pipe. You can add pipe here and add, for example, add here. Minus is probably not needed. It should work the same as addition, so with the pointers as well, but I do not use minus for pointer arithmetic. I think so this doesn't matter if it doesn't work during this transition stage. And then we can add the same actually to the LNTAC binary expression here. So we just add the pipe here and we generate then an add instruction. Yeah, I understand currently that I do not need this sum create function, at least at this stage, because I would just use the sum function if I encounter the pipe operator. So let us actually remove this nonsense. Again, this will be binary create and this will be binary create. And we will use sum create only for the addition, only for the pipe addition. That works. It should be now possible to use the pipe instead of add. And this works fine as well. Let us add a comment here that pipe can be used as alternative to the binary plus. For point arithmetic. Be used as binary plus for point arithmetic. Okay, and we compile it and do a final test, and I will stop it here, and I will think how I can implement this at point arithmetic with types of pointers that are not 1 byte long, so that we implement addition and subtraction correctly. But for today I will leave it here, and we will continue later and do point arithmetic with this new pipe operator.